I am now asking a hidden Markov model question, and we're given the following hidden Markov models with two internal states, with the probability of transitioning to either side is 0.5, and the probability of staying is therefore also 0.5. This hidden Markov model has two possible measurements or observations, x and y, and the probability of observing x or y depends on what state the hidden Markov model is in. For A, it's 0.1 for x and 0.9 for y, and for B, it's 0.8 for x and 0.2 for y. Now let's assume that the initial probability distribution at time 0 is a half for either of the two states. I would like to know what's the posterior probability of being in A at time 0, given that we observed x at time 0 and not y. What's the posterior probability of state A at time 1, given the observation of x at time 0? And what's the posterior probability of A1 given that we observed x at time 0 and x at time 1? Which just means two consecutive x's. We obtain P of A0 given x0 through Bayes' rule, which should look very familiar at this point. P of x0 given A0 is 0.1 multiplied by 0.5, and down here we get 0.1 times 0.5 plus the same probability for B0, which is 0.8 times 0.5. As is easily seen, the 0.5 falls out, so we get 0.1 over 0.9 or 1/9, which is the answer for the first question. In the second question, we apply total probability. This is the formal definition of total probability, which is the probability of A1 given that we were previously in A0 times the probability of being A0, and the same for B0 before, as you might easily recognize. Now it turns out this hidden Markov model is a funny one. Every single time step it completely mixes. The probability of transitioning is the same as staying in the same state, so we completely forget the history. So therefore the answer to this question would be 0.5 or a half. But let me just derive it formally. The transition probability of going from A0 to A1 is 0.5 times our prior probability, which is 1/9, and we get the same 0.5 over here times our prior probability of 8/9. And if you work this out, you'll find that 1/9 plus 8/9 is 1, and therefore the 0.5 is the final result. This is a really unusual Markov model where there's no memory retained from one step to the next. This also means if we now observe x again and look at this probability over here, we can apply the exact same logic as before, because now our prior is still 0.5, and we get 1/9 again, with the exact same argument as before. Before observing x0, we had a 0.5 chance of being in A, and it went down to 1/9. Here we still have a 0.5 chance of being in A, therefore the exact same math gets us down to 1/9.